Exercise 2137 is asking you to make several different compounds from only two starting materials. Acetonitrile, which is a very common molecule that you'll find in organic and biochemistry labs. It's used as a polar aprotic solvent. Sometimes if something doesn't dissolve in water, you might try dissolving it in acetonitrile. They especially use it, you can see it used sometimes with HPLC, high pressure liquid chromatography, to separate proteins or amino acids. So it's a common molecule, acetonitrile. It's very small. It's a 2-carbon nitrile. And then carbon dioxide. So we can use those two common, inexpensive starting materials to make all sorts of things. And in this exercise, we're going to try to make 2-butanol from just those two starting materials. Now, in terms of synthesis, the difference between these two possible starting reagents is the number of carbons. The acetonitrile has 2 carbons, and the carbon dioxide only has 1. So if our final product has only an even number of carbons, then we can just make it from acetonitrile. But if it has an odd number of carbons, then we'll have to use carbon dioxide. That's our way of adding an odd number of carbons in this exercise. Well, in this first one, in 2-butanol, we only have 4 different carbons. And so we're really just going to make this only from acetonitrile. We don't have to use any carbon dioxide at all here. So you can sort of think of this as divided into two 2-carbon branches. Well, something you'll notice in both of those parts is there is no nitrogen. And there is nitrogen in acetonitrile. Acetonitrile would look like this, and if you had the skeletal structure. So that's the CH3CN. So one way you can get rid of the nitrogen is just to hydrolyze it. And we've seen this reaction before. If you treat it with H3O+, that turns it into a carboxylic acid. So we end up with ethanoic acid or acetic acid, vinegar. Okay, so what can we do with this? This definitely looks more similar to the kind of stuff we want. Now, one thing we would notice is that we have to form a carbon-to-carbon bond. And that carbon-to-carbon bond that carbon-to-carbon bond would suggest something like a Grignard reagent, some sort of carbon nucleophile. So how can we make that? From ethanoic acid. Well, the first thing we have to do is to get rid of this carbonyl, because a Grignard reagent, if we had a 2-carbon Grignard reagent, it would just be 2 carbons and then MgBr. Now, if you notice, that has no double bonds to oxygen there, so we'd have to get rid of that. And we can do that by replacing those bonds to oxygen with bonds to hydrogens, and that's reduction. So we can treat it with excess strong reducing agent, lithium aluminum hydride, and then just follow that up with water to stabilize any of the charges. And what you'll be left with is a primary alcohol when that's done. You replace the 2 bonds to oxygen with 2 bonds to hydrogens. The hydrogens are coming from the lithium aluminum hydride. So now we have ethanol, drinking alcohol. And if we're trying to get our Grignard reagent, we need to replace that OH with a Br. And this is something you'd want to remember from the alcohol chapter. You can treat that with a molecule called phosphorus tribromide, and that replaces the OH with a Br. It really does it through a sort of SN2 reaction. Let me draw that out just for a second, and we'll go back to the synthesis. But what it looks like is it works almost in a similar way as thionyl chloride, in the sense that this phosphorus compound ends up making the oxygen a good leaving group. The oxygen attacks, the slightly negative oxygen attacks the slightly positive phosphorus. All those bromines are more electronegative than the phosphorus, so they pull electron density away from it. The phosphorus becomes slightly positive. And at the same time, one of the bromines leaves. So basically an SN2 reaction. Now what you end up with after that step is the oxygen, but now it's bonded to a phosphorus with 2 bromines. And this whole thing can function as a good leaving group because that oxygen has 3 bonds and therefore a full positive charge. So the bromine that left can sort of swoop in and kick that off, do another SN2 reaction, and you end up with the bromine on the carbon chain and some weird phosphorus compound. But that's floating around the solution as a waste product. This is the product we would isolate and use. So long story short, if you treat an alcohol with phosphorus tribromide, it replaces the OH with a Br. Okay, so let me clear all of this. So we treat that with phosphorus tribromide, we end up with that. And from there we can make our Grignard reagent. Remember, that was our goal over here. To make this carbon-to-carbon bond, we wanted a Grignard reagent. We have the bromine now. All we have to do is dunk some solid magnesium in there, and we have our Grignard reagent. Okay, well, so much accomplished there. How do we get, so that's this left part. What do we want on the right? What would we want a Grignard reagent to attack there? Well, we know we'd have to have the 2 carbons. It would be nice if we had an oxygen there, and if we want the Grignard reagent to attack, it would be nice to have a good electrophile there. But we don't want it to be a carboxylic acid derivative like an acid chloride, because then it would add twice. So we really would like that to be an aldehyde. This way the Grignard reagent will only add once. So how can we turn acetonitrile into acid aldehyde? Well, we can take the acetonitrile and again hydrolyze it so we get to the carboxylic acid. That at least gets rid of the nitrogen. Once you have the carboxylic acid, in this molecule that we have, there are 3 bonds to oxygen, and the one that we want, there's just 2, so that's a reduction. Now, if you use lithium aluminum hydride, it will reduce it all the way down to the alcohol, just like it did here. So instead, we'll use a weak reducing agent, and we've seen this one several times before. It's a lithium aluminum trialkoxy hydride, followed by water. And what that does is that takes the carboxylic acid down to the aldehyde. It only adds 1 equivalent of the hydrogen. Now, the truth is, if you wanted to increase the efficiency of that reaction, you might want to turn this into an acid chloride first, because this hydrogen nucleophile is not that strong. So you could use thionyl chloride to turn the carboxylic acid into an acid chloride. And once you have that really strong electrophile there, you can use even just a weak hydrogen nucleophile like this. And there are other ways you can do this. You could, for example, use lithium aluminum hydride, get it down to the alcohol, and then use a weak oxidizing agent like PCC, and that will give you the aldehyde also. So there are several ways you can do this. This is one possibility. Okay, well now we just have to put our 2 pieces together. We can take our Grignard reagent and react that with our acid aldehyde. the carbon nucleophile there, the carbon nucleophile attacks the carbonyl carbon, kicks the pi bonds up, and now we have 4 carbons connected to each other. The third one is an O minus. So if you were numbering these to keep track, 1, 2, 3, 4, that's 1, 2, 3, 4. So then you just have to treat it with a little bit of water to do a proton transfer to stabilize that negative charge, and you'll have your product, 2-butanol. So it's a little bit of a slog. You first have to turn, in each of the cases, we notice we don't have any nitrogen there. So, okay, starting from the beginning, we noticed we had 4 carbons. That's an even number, so we knew we only had to use acetonitrile. We didn't have to use carbon dioxide. We cut the carbons in 2 and looked at the 2 pieces. We saw that we had to form a carbon-to-carbon bond between them, and so we knew we would need a carbon nucleophile. The part that did not have a functional group on it, we knew we wanted to turn into a Grignard reagent. To get that out of acetonitrile, we first had to get rid of the nitrogen. So we did a hydrolysis, and we got the carboxylic acid. Now that had lots of bonds to oxygen, and the Grignard reagent doesn't have any, so we replaced bonds to oxygen with bonds to hydrogens by using a strong reducing agent like lithium aluminum hydride. That gave us the alcohol. Now we needed to get rid of the OH and turn it into a bromine. And to do that, we used phosphorus tribromide. Once we had the bromine there, we just dunked some solid magnesium in, and that gave us our Grignard reagent. So much for the half of the molecule that did not have a functional group. The other half that did have a functional group, we saw that we wanted to be an aldehyde. So starting with acetonitrile, we could get the aldehyde first by doing a hydrolysis that gets rid of the nitrogen, and then we want to reduce it. And we saw that we wanted to reduce it just once, not all the way down to the alcohol, but to the aldehyde. So we used a lithium aluminum trialkoxyhydride followed by water. But because that's a weak reducing agent, we had to strengthen our electrophile, and we did that by turning the carboxylic acid into an acid halide using thionyl chloride. Once we had those pieces, we treated the Grignard reagent, carbon nucleophile, with the acid aldehyde. It attacked the carbonyl carbon. We got our new carbon-to-carbon bond, and we just stabilized the charges with water. And that is amazing how much you can do with just one molecule, and a simple one at that. Okay, how about B? Well, in B, one thing you will notice is that we have an odd number of carbons. There's 1, 2, 3, 4, 5 carbons. And what that means is that we're going to have to use carbon dioxide. So we're going to use, in this reaction, we're both going to use acetonitrile, and we're going to use carbon dioxide. So you have 1, 2 carbons. After the first 2 carbons, a break. You can't add more than 2 at a time. And next, you can have sort of the other 2 carbons on the other side. Now the reason why I'm putting the oxygen with the carbon that's alone, as opposed to one of the carbons at the end, having that one be the one that's alone, is because the oxygen is on carbon dioxide. And so we want the carbon that has the oxygen on it to be the one that's in the middle. And carbon dioxide has a carbon that's all alone. So we want this carbon to be all alone. Okay. Well, the thinking here is actually very similar. We know we have to form carbon-to-carbon bonds, and therefore we need Grignard reagents. So we can follow a similar process of reasoning as before. We can get rid of the nitrogen on the acetonitrile by doing a hydrolysis. That will turn it into a carboxylic acid. Once we have the carboxylic acid, we can reduce it using excess lithium aluminum hydride. We're replacing the bonds to the oxygen here with bonds to hydrogens. So far this is exactly like the last one, just making the Grignard reagent. That gives us the alcohol. We can replace the OH on the alcohol with a bromine by using phosphorus tribromide. And then we just dunk some solid magnesium in there, and we have our Grignard reagent. Okay, what's different here is what we want this Grignard reagent to react with. At first, we just want to add one carbon, and we can do that by reacting the Grignard reagent with carbon dioxide. So that will give us our 3-carbon piece. So if we treat this with carbon dioxide, the oxygen here, or sorry, the carbon nucleophile in the Grignard reagent will attack the carbon and carbon dioxide, break open a pi bond, and what we'll be left with is a 3-carbon molecule with a double bond to an oxygen, single bond to an O-. So a carboxylate, and we can stabilize that by using some water or some acid just to do a proton transfer. So that gives us a carboxylic acid with 3 carbons in it. Now, ultimately, we want, in this molecule, we want to attach another ethyl group here. Well, what we need to do that is another Grignard reagent, another 2-carbon Grignard reagent. So we can go through the same process as above, and here I'll just do it vertically on the other side of this page. We can take acetonitrile, get rid of the nitrogen by doing an acid-catalyzed hydrolysis, turns it into the carboxylic acid, and then we can reduce it, right? We're trying to get this to look like this Grignard reagent, so we need to get rid of all these bonds to oxygens, so we reduce it first with excess lithium aluminum hydride, followed by just water to do proton transfers to stabilize any charges there. And that would give us the primary alcohol, which we could treat with phosphorus tribromide. We drew the mechanism for that before. That uses 2SN2 reactions to replace the OH with a Br. Then we just dunk some solid magnesium in there, and we have our Grignard reagent. Okay, so now we want to react this Grignard reagent with this carboxylic acid. But the Grignard reagent, the negative carbon on this Grignard reagent would just steal the acidic hydrogen in this. Not only that, but if you have a carboxylic acid derivative, like if you turn this into an acid chloride, then the Grignard reagent is a strong carbon nucleophile, and it would add twice. And as you can see here, we only want it to add once, because we want just a 5-carbon chain. We already have 3 carbons here, we have 2 here, we only want it to add once. So we need to reduce this down to an aldehyde, because then the Grignard reagent will only react once. Well, you can reduce it down to an aldehyde the way we did before. You could treat this with cyanyl chloride and then reduce it with a lithium aluminum trialkoxyhydride. So that's one way. Let's do something different here just for a change. Another thing we could do to turn this into an aldehyde is treat it with a strong reducing agent, excess lithium aluminum hydride, and then followed by water to stabilize any charges, and then that will just give us the alcohol. And then we can oxidize the alcohol to an aldehyde using a weak oxidizing agent like PCC, pyridinium chlorochromate. So that would give us this aldehyde. Pyridinium chlorochromate changes primary alcohols into aldehydes. Then we can take our Grignard reagent and react it with this aldehyde, so you have your carbon nucleophile being stabilized by the magnesium bromide that attacks the carbonyl carbon, kicks the pi electrons up, and we would have a 5-carbon chain, 1, 2, 3, 4, 5. So a 5-carbon chain with the oxygen on the 3rd carbon. It would have a negative charge at first, and so we would just have to stabilize that by doing a proton transfer from water. Okay, and so that is a sort of plan for making this transformation, for making that molecule from acetonitrile. It's kind of long, but also kind of beautiful when you stand back at it, almost like a ballet. So to review that thought process that we went through just one more time here, we saw that we had 5 carbons in the carbon backbone. That meant that we both had to use acetonitrile, which has 2 carbons, and carbon dioxide, which has 1. We have to use carbon dioxide in order to make the number of carbons we have odd. We have 5. So we saw that there's no nitrogen in the molecule. So if we use acetonitrile, for sure we had to do an acid-catalyzed hydrolysis to turn it into a carboxylic acid. When we looked at this, we knew that these carbon-to-carbon bonds that we're forming are going to be formed by Grignard reagents. And so for one of these, we know that the part that does not have the functional group on it, that part would be the Grignard. So we want to turn this acetonitrile into a Grignard. We turn it into the carboxylic acid. In the Grignard reagent, there are no bonds to oxygen, so we have to start replacing the bonds to oxygens with bonds to other things. And at first we replace the carbonyl with bonds to hydrogen. We do that by using a strong reducing agent like lithium aluminum hydride. Don't forget to follow that up with water to replace any protons, to do proton transfers to stabilize any charge. That gave us the alcohol, primary alcohol. We replaced the OH here with a bromine by using phosphorus tribromide. Once we have the bromine, we can dunk some magnesium in there, and that gives us our Grignard. Now, here we wanted to attach the Grignard to the 1 carbon that had the oxygen on it. That's going to be the carbon dioxide. So we reacted the Grignard with the carbon dioxide, got a carboxylate, and stabilized that with a proton transfer. So that gave us a carboxylic acid that had 3 carbons, crucially. So then we wanted to form this other carbon-to-carbon bond, and we knew that that was going to require a Grignard reagent too. So we went through the same process to get the Grignard reagent. Get rid of the nitrogen by doing acid-catalyzed hydrolysis. That gives us the carboxylic acid. Get rid of the bonds to oxygen by using an excess lithium aluminum hydride, strong reducing agent, followed by water to stabilize charges. Replace the OH with a Br by using phosphorus tribromide. And once you have the Br, dunk some solid magnesium in, and that gives you your Grignard. Now, once you have the Grignard, we wanted to react it with this other molecule. We wanted to attach, but we only wanted it to attach once. We wanted to have 5 carbons. We didn't want 2 equivalents of the Grignard to add. That would give us 7 carbons. So we only wanted it to add once. So we wanted this to really be an aldehyde, because this would add twice to carboxylic acid derivatives. And honestly, if you treat a Grignard reagent with a carboxylic acid, it wouldn't attack as a nucleophile. It would just steal the hydrogen from the acid. It would act as a base. So we wanted to turn this into an aldehyde. In other words, we wanted fewer carbon to oxygen bonds. One of the ways we saw we could do that is by using excess lithium aluminum hydride in water. That takes it down to the alcohol. And then we could use a weak oxidizing agent like pyridinium chlorochromate. That takes it to the aldehyde. Once we have that aldehyde, we can treat it with our Grignard. That attaches the 2 carbons, forms that new carbon-to-carbon bond, and then we just used a water wash to stabilize that negative charge. And that gave us our product. So, sort of beautiful there. Okay, now, for C, if you notice, C, you can actually make C from A. Now, I'd be happy to walk through this whole process for A again, but because we walked through it in this video already, and the video will be long enough with that, let's just start with C. Let's start with what we got from A. Let's start with this product. So if you want to know how to go back and make this product for A, rewind the video. You'll see how to walk through all this. Let's start with this 2-butanol. So if you have 2-butanol, that's our product for A. You can sort of see that hidden inside of this carbon chain. So you'd have 1, 2, 3, 4. So you can sort of see how you have 1, 2, 3, 4 carbons, and the OH is on carbon number 2. So 2-butanol. The only new thing here is this other group, this new carbon-to-carbon bond. Now, that new carbon-to-carbon bond we can make with a Grignard. So we can do the classic old setup that we've done several times now. Use acetonitrile, because we're only adding 2 carbons. We can get rid of the nitrogen there by doing an acid-catalyzed hydrolysis. That turns it into the carboxylic acid. And then we need to get rid of all those bonds to oxygen, so we can use excess reducing agent, lithium aluminum hydride, followed by water to stabilize any charges. That gives us the alcohol. Replace the OH with a Br by using phosphorus tribromide, and then dunk some solid magnesium in there. And that gives you your Grignard. Now, we can make that react here by turning this into a good electrophile. And we can turn this into a good electrophile by oxidizing that bond. If we used sodium dichromate, Na2Cr2O7, in an acid-water wash, so water and H2SO4, sulfuric acid, that will turn this secondary alcohol into a ketone. And once you have the ketone, you can react it with your Grignard. The 2 carbons, one of them will act as the nucleophile, this one here. That would attack the carbonyl and break the pi bond. And what you'd have there is this molecule here. And you just have to stabilize that negative charge by doing a proton transfer from water. And notice what we have. We have a carbon chain that is 1, 2, 3, 4, 5 carbons long. So let me draw that in a conventional way. 1, 2, 3, 4, 5 carbons long. On carbon number 3, we have a methyl group. So if I number this, 1, 2, 3, 4, 5. Carbon number 3, we have a methyl group. And on carbon number 3, we would have our oxygen, and after a proton transfer from water, an OH. And that, notice, is what we have here. You have the 5 carbons. And on carbon number 3, a methyl group and an OH. So you would first make 2-butanol in the same way that we did for A, 2-butanol, turning acetonitrile first into a Grignard, which we've seen a whole bunch of times, and then turning it into an aldehyde, and then reacting those two things together and treating it with water. That gives us 2-butanol. Once we have the 2-butanol, we just oxidize it using a strong oxidizing agent like sodium dichromate, and that gives us a good electrophile, and then we make another Grignard. React the Grignard with that electrophile, and that gives us our new carbon-to-carbon bond. And then we just stabilize the charge with a water wash. Okay, now for D, in D, you'll notice that it's actually similar. But here, because we don't have the 1, 2, 3, 4, 5, because no matter where we go, we can't get the 4 carbons, it's not going to be the same process as in A to get the backbone. So instead, we can get a 5-carbon alcohol, and then we'll treat that with a Grignard. So what we can do here, we see that we have, no matter how we cut it, we see that we have 5 carbons. And so if we can have no more than 2 at a time. So we can sort of cut this up a lot like what we did for B. And actually, if you make B, you go through this whole process, and you make 3 pentanol, if you have 3 pentanol, oops. So if you go through the same process we went through for B, so you go through all those beautiful machinations to get this product. Once you have that, and if you want to rewind and see how we went through that, once you have that, what you got for B, you can turn it into this. Because all we need to do is to form a new carbon-to-carbon bond. We need to add 1 more ethyl group on there. Well, that means we just need a Grignard. So we could use acetonitrile, do an acid-catalyzed hydrolysis to get rid of the nitrogen. That turns it into the carboxylic acid. Get rid of those bonds to oxygens with a reducing agent, so excess lithium aluminum hydride, followed by a water wash to do some proton transfers to stabilize charges. That gives you the alcohol. Replace the OH with a bromine by using phosphorus tribromide, and then dunk some magnesium in there, and that gives you your Grignard. So then you just need something for your Grignard to attack. We want it to attack this carbon. We need to make this more electrophilic. We can do that by doing an oxidation. So treating it with a strong oxidizing agent like sodium dichromate, Na2Cr2O7, in an acid water wash, H2O and H2SO4. And that turns that alcohol into a ketone. Once you have the ketone, you can treat it with your Grignard. So that's 2 carbons. One of them acts as a nucleophile that attacks the carbonyl, kicks the pi electrons up, and what you end up with is this molecule here, which, if you stabilize that charge with a proton transfer from water, gives you your product, the one that you want. So you'll notice that's our product here. So once you have the molecule that we made in B, and that was something of a long process, but once you have that molecule, you can make another equivalent of the Grignard, oxidize this, and have the Grignard react with the carbonyl carbon in the oxidized ketone. So that is this sort of creative puzzle of exercise 237. This puzzle where you start with very cheap and expensive things, and you use the same thing, but you use it in different ways to create ever more complicated products. It's remarkable to think how much you can make from just one molecule as your starting material. So this is a sort of exercise in puzzling, in solving puzzles and creativity. And it's also a lesson in ingenuity, because it shows you how much you can do with very, very little. So, we will continue the multi-step syntheses of carboxylic acids and their derivatives in another video.